if you were using a book that doesn't have this as its own section, I would look for this where you do the large size confidence intervals. Now this, the idea behind this is, let's say that you want to construct a confidence interval with a certain percentage. In other words, you want a level of 95%, and you want to predetermine what you want the margin of error to be. Let's say you want it to be a specific value. So the question then lies, can we come up with the sample size necessary to meet those requirements? And yes, we can. And the formula we use just involves your margin of error formula. Now we're back using Z's and not T's for this. And you do a little algebra to this, which is not required. I could show you, but you come up with this formula right here, where n, coming from this formula, would be the critical value z times the standard deviation divided by the margin of error, and all that squared. Don't forget to square that. I often find that students will forget to square it on an exam. And this is a good policy, always round up to the next integer. That makes it a better result. Going up means you're guaranteed that you'll meet the margin of error requirements. So similar to finding the class width that was talked about earlier in the course, you round up on this. So for example, if you calculate 49.3, the best answer would be 50. 50 is a better answer than 49. All right. So like I said, this will be a short lecture since many books already contain this topic within the large sample section. So let's see, determine the minimum required sample size needed if you want to be 99% confident that the sample mean is within 2 units of the population mean, given that the population standard deviation is 3.4. Assume the population is normally distributed. Now we're looking for something a little bit different. Now we're looking for what triggers us to knowing what the value E is. And that within right here, the within is your clue as to what your margin of error would be. So that statement, part of the statement right here, within 2 units, that right there, that tells us that's my E, that's my margin of error. 2 above, 2 below. So now we don't have degrees of freedom. We're dealing with Z. So the 99%, there's those values that are on that chart I'll give out. So no looking up that other chart, 99% for Z would be 2.575. Standard deviation is 3.4. So this is a real easy calculation. You just take your critical value, the 2.575, times that standard deviation of 3.4, divided by 2. Don't forget to square it. So you see what I've done in the calculator box here. There is not a built-in program in the calculator that does sample size like it does for the Z interval and the T interval. But this calculation is so basic, I don't think it's really necessary anyway. It's pretty easy to do. So I come up with 19.16 blah, blah, blah. These answers are always going to be integers because the sample size is going to be an integer number. You take a sample, so you round up. So we would want a sample size of 20 to meet our requirement for a 99% confidence interval to have a margin of error of 2 based on that standard deviation, 3.4. So let's look at the next example. Cholesterol contents of cheese. A cheese processing company wants to estimate the mean cholesterol content of all 1-ounce servings of cheese. The estimate must be within 0.5 milligrams of the population mean. Determine the minimum required sample size to construct a 95% confidence interval for the population mean. Assume the population standard deviation is 2.8 milligrams. And then B says repeat part A using an 88% confidence interval. So the key phrase here must be within 0.5 milligrams. That is your margin of error. So my critical value, so there's your E is 0.5. The standard deviation is 2.8. The critical value for 95% Z is always 1.96. No degrees of freedom involved here. So we take the formula that says we have the critical value multiplied by the standard deviation, divided by the margin of error 0.5, square that. You get 120.47, as you can see in the calculator box right here. We round that up to 121. So we need a sample size of 121 to meet that requirement. Now let's look at part B. Now, part B, the 88% confidence interval, that goes back to the video that I made for confidence intervals, large samples. Now, small sample T's, we're only going to work with the confidence levels that are on that T chart. But I showed you an example on the large sample video where I did one for, I believe it was 82%. So if you go back and look at that, you'll see how to do this. So we have to actually work a little bit for this one to get our Z alpha over 2. You know, when it's 90, 95, and 99, we already have those numbers pretty much standard issue. So for 88%, I go 1 plus 0.88. So it's 1. You go back and look and you see it's 1 plus confidence level, all divided by 2, and that's 0.94. So if you're using the chart, you see 0.94 would be right between 9394 and 9406. So the best answer would be to average these two numbers. 1.5. Oh, that's a mistake right here. That should just say 1.5. It's in the 1.5 row. So together that makes 1.55, and then that makes 1.56. Add those together, divide by 2, you get 1.555. That's the only time we'll average them, if it's right in the middle of the two numbers. Other than that, we would always pick the closest number. That'll make it a little more accurate. So that was the tricky part of this problem, was finding that critical value. So now we have n equals that 1.555 that we just found times the same 2.8 divided by the same 0.5 as part A. All that squared, you get 78.6, and round that up to 76. Let's look at this example. What sample size is needed to obtain a 90% confidence interval for the mean protein content of meat if the estimate is to be within 2 pounds, there's your margin of error, of the mean value. Assume that the population variance is 49 pounds. All right. Trying to trick you here. Variance. Always remember, most of the time it's going to be standard deviation, but if it gives you variance, you just have to take the square root to get the standard deviation. So we won't use 49. We will use the square root of 49, which is 7. So the within 2 pounds tells me my E is 2. And then the 90% Z value is automatically 1.645. So I think the tricky part about this problem is remembering to take the square root of 49. So here's our n. It's 1.645 times 7, all divided by 2. That comes up to 33.15, which we will round up and get 34 as our answer. So that one was a little sneaky with that variance instead of standard deviation, but keeps us on our toes, makes us have to think a little bit here, because this section was getting too easy. So, all right, let's see what we got down here. Looks like I got one more example where it's not worked out, so you get to watch this one being worked out. I already have the answer there, so let's see how that works out. In the manufacturing process, we are interested in measuring the average length of a certain type of bolt. Past data indicates that the standard deviation is 0.25 inches. I'm going to call that sigma, but it's not a big deal if you say it's S. It's not going to hurt anything. There's only one. There's not like we're making a distinction that the formula is not different. In other words, it's still going to be a Z. We'll still, assuming that's a sigma, which we will. 95% confident, so within 0.02 bolts of the true mean bolt. So there's your E's, 0.02. Now be careful when you put this in the calculator. I've seen people do 0.2. 95%. My Z is 1.96. So all we do here is use my formula. N equals the z of 1.96 times 0.25 divided by 0.02 squared. Don't forget the square. 1.96 times 0.25 divided by 0.02 squared. Oh, hit the wrong button. Squared. There we go. Well, 600.25. I like that answer because I'm going to round that up and I'm going to call it 601, which is answer D on here. Perfect. So I believe I have no more examples here. I believe that concludes the lecture on determining the required sample size.